Good afternoon, everyone. Thank you for joining us again for this RC design class. Today's Thursday. We're going to have a little bit longer session today. Before we get started, I want to get a survey going on right now about our situation with the career fair next week and also fall break. And I just heard from Kenny that fall break is relatively new. And last year we were in quarantine, so pretty much did not get a break really. So I hope that you guys will enjoy the break. And considering this career fair situation, now to solve this problem, I propose we do this way. We will stay a little bit longer today to teach, to finish about this design with singular reinforced section with unknown section sizes today. I'll try to finish at least. And then we'll talk about how we do the doubly reinforced section on Monday and Wednesday. And I try to cut the lecture a little bit short on Monday, Wednesday, and also try to make it easy for you guys to go to the career fair. I decided and I propose here, and I need to hear your feedback. That is that we do this online on Monday, Wednesday, so I can have a recorded video for you guys to watch. And that is if everybody's on board. So I need to show the hands that if you guys are okay for us to do 2 more online lectures on Monday and Wednesday, and I'll cut them short so you guys can get to career fair and also watch the video. Now, if you're up for it, please thumbs up or anything, clapping hands, so I can get a count of it. Okay, I see a couple. Okay, let's do a little bit more. Let me see how many. Okay, got 2 full screens. Okay, panel number 1, majority yes. Panel number 2, majority no. Panel number 3, majority yes. Okay, keep going, 16, okay, 15, okay. Let me ask again, okay, in case you just freshly joined. Now, if you're agreeing us to do a shorter online version Monday and Wednesday, I can have recorded video post on YouTube so you can watch later to make it easy for you guys to go to career fair. Please thumbs up in the chat or on the screen so I can see them. Okay, all right, okay. All righty, okay. Okay. Few more, okay. All right, I got a peak number about 27 plus the 8 or 9 that was giving me thumbs up previously. I think we're halfway over the class roster. So I think the answer is yes, we can do a shorter lecture on Monday or Wednesday, and it will be recorded and put on YouTube. And we'll return to class after fall break, which is the Monday after the fall break. Let me just double check. And that is October the 4th on Monday. Okay, in person, returning to classroom on Monday 4th. And I'll finish my traveling next week as well anyway, so we should be good. And that's that to solve our career fair situation and also accommodating the fall break missing lecture on Thursday. All right, so that's that. Now, with exams, I will do a review session on Tuesday in the afternoon, that is from 3 o'clock, and it can be extended on the needed basis from 3 p.m. to 7 p.m. I have 4 hours office hours. What I will do is that I will post a Zoom link and also sit in my office, so you can choose to come stop at my office or you can Zoom in. Either way, it's going to be fine with me. So I talk about what type of problems you might see in a review session. And I'll try to book a room as well if I are able to book a room, because right now booking room is a little bit difficult because we have to consider the accommodation and know that. But if I manage to book a room, I'll let you know, and we'll do this review session on Tuesday in the classroom setting. But worst case scenario, I'll be in office. You can stop by or you can Zoom in. Okay, this is for review for the exam number 1. And this is additional review lectures, kind of not official, but will benefit you, I think, if you attend. Okay, so let me just put out there 3 p.m. Tuesday. And again, I will send an email for us, and you guys should have it in your calendar that you can come in. All right, any question about the first exam review? And I have a few questions. First of all, I got a question from Kenny. Let me read out from chat. Will we get all the exam or practice problems for the test? Yes, I'll post a practice test today, later today, Thursday in the evening. That's the previous year's problem, maybe one set exam problem, so you can work on it. And next week, a little bit more. The week after next week, when we start a review session, bring your question. we can address that. Okay. And I got a second question from Sophie. Is that next Tuesday or Tuesday before the test? It will be Tuesday before the test. Will be October the 5th. October the 5th. Okay. And Kenny is the same question. The answer that's October the 5th for the office hour before the exam. But let me say this, if you have any burning questions, if you have any urgent questions, email me. We can find a time to chat and we can solve those problems. Okay. All right. Now I have roughly made a problem now with the first exam. And I can tell you right now, it's going to be 4 problems instead of 3. It's going to be 4 problems. So number 1 will be multiple choices. Number 2 will be a filling a blank together with solving the problem together. So it's like a hybrid problem. Essentially, I can tell you right now, it's about detailing of the bars, right? How you're going to put the bars in, what is the minimum beam width, what is the clear spacing for concrete cover, spacings for the bars, how you fit them in, okay? Problem number 3, we'll talk about how to do analysis on doubly reinforced bars. Problem number 3, analysis on doubly reinforced bars. Problem number 4, a design problem. Problem number 4 will be a design problem on singularly reinforced section. Now for the singularly reinforced section problem, it can be both, which means it can be a known section designed for reinforcement, or it can be designed for unknown section. So it can be either one, all right? So chances are, we'll probably give you a little bit tip on how to provide the geometries, but you still have to run through the whole 9 yard when designing the problem 4, okay? So let me repeat, all right? There will be 4 problems in the first exam. Number 1 will be multiple choices, you know, the knowledge we gain from chapter 1 to chapter 3, a little bit miscellaneous informations. Now, problem number 2 is going to be detailing, bar detailing, how you're going to fit the bar in, what will be the beam width, and all that nice details. Number 3 will be an analysis of doubly reinforced section. Analysis, when I say analysis, it's really trying to find the moment capacity for the doubly reinforced section beam, all right? And the last one, but not least one, is the design for singular reinforced section. And we just finished talking about design with singular reinforced section with given section. Today, we're going to talk about design of singular reinforced section without known dimensions of the section. But in the last problem, you might be tested on both, which means either or, okay? Either or, all right? Okay, any questions about what we have announced so far? Any issues with doing online, short lecture online Monday and Wednesday to accommodate the career fair? Any questions, any problem with that? Okay, any issues with review session next Tuesday, the Tuesday after next week, October the 5th from 3 p.m. I'll be on campus as well and doing the Zoom as well. So you can choose review October 5th, Tuesday. Is that okay with everybody? 3 p.m. You have conflict, you let me know. If you need additional session, email me, we can arrange that, okay? Last question about the first exam, 4 problem. This is gonna be 3rd time I'm saying this. 4 problem, number 1 be multiple choices, about 12 small multiple choices, probably give number 1. Number 2 will be a detailing problem. Number 3 will be analysis of doubly reinforced section. Number 4 will be design for single reinforced section. Any question about number 4? Sorry, any question about exam number 1? Anything? Okay, all right. Last, I got a question from Adam. Can you post on Canvas what we are allowed to bring to the exam? Yes, I will do that, but let me tell you guys right now, you're allowed to bring a A4 creep sheet, front and back, okay? Front, back. You're allowed to bring your calculators. Yes, definitely yes. You're allowed to bring scratch papers, and I'll provide, okay? I know I'll provide. If you bring your own scratch paper, I need to take a look at it to make sure nothing's on them, all right? Okay, A4 creep sheet. A4 is a printing paper. It's roughly 8.5 by 11 inch size. Yes, so we can write anything on it, front and back. You can write anything on it, front and back. And last but not least, you're allowed to bring ACI code 318.9.19. So that code has to be printed out version or the hard copy version you bought. Cannot be on an iPad, cannot be on the phone, cannot be on a laptop. All right. Okay, no lecture notes are allowed. No lecture notes are allowed. No homeworks are allowed. These are only items allowed. All right, and I don't want to see any laptops. I don't want to see any iPads. I don't want to see any iPhones during the exam time. The exam will be in classroom, in classroom. Okay, same classroom we use for lectures. That exam will be October the 7th in the afternoon, starting from 1 p.m. Okay, we have roughly, I'm thinking right now, 2 hours to solve for problem. That is 25 minutes per problem, which is more than enough. Okay, all right. Any other questions, folks? Anything that clear? All right, Xander, any question from you? You okay? Xander, are you there?
His microphone doesn't work. He's sitting next to me though.
Okay, that's good. We'll just mute you a little bit because I don't want to keep the flow going. Okay, that's all right. Don't worry about it. Okay. Okay, so I think that's enough for the announcement. Like I said, today is going to be a little bit longer lecture, so let's just get on to it. Okay, so let me just share screen and do the air share. Okay. All right, so we talk about design for a, yes, we talk about the design for a known section, right? Known section. So that is, if we were given the geometry of the section, we need to determine the reinforcement. So a quick review of what we have done so far, right? So you go from top, and this is example, we show a simply supported beam that have both the dead load and light load exerted on it. Okay, to save you the trouble for the first example problem, we tell you that the applying moment is 145 kip-foot. That is a fixed number. You don't have to do any calculation for it. The section size is 12 by 24, and we're trying to find a reinforcement. So what did we do, right? We start from design philosophy, phi mn has to be greater than mu, okay? Then we guessed, we estimate the phi, which is 0.9, all right? Then we use AS and has to be greater than or equal to this number here from the design equation. And don't forget, we estimate the ds minus half a by 0.9 ds, 90% of the depth. And then also we said for one layer reinforcement, ds equal to h minus 2.5. For two layer, ds equal to h minus 3.5. Okay, so for any cases in your design problem, for example, exam number 1, you start from one layer unless I specify in the problem that 2 layers or multi-layer reinforcement might be needed. Okay, usually it's 1 layer. Okay, then from there, you go on calculate your first estimation of AS. You got this AS area equal to 1.67 inches, and then we proceed to recompute the effective compressive zone A. Effective compressive zone A. So how to calculate effective compressive zone A? We use the same equation. Compression has to be equal to tension. The 0.85 prime CAB equal to ASFY. Then I got effective compressive zone A right here. Okay. Now, once you got effective compressive zone A, what you need is use that A to recompute your liver arm, that is JD or DS minus half A, DS minus half A. Okay, so with that, we confirmed or arrive at different AS. So pay attention, folks. We're doing AS twice, essentially. We did AS without knowing anything, right? We made a guess. Most important, we made a guess here, this step, ds minus half a approximately equal to 0.9 ds. This is approximate. We bring this value in and then calculate the new A and then recalculate the AS. That's what we did. And once we have AS, second calculation, we can start selecting bars. So how do we select the bars? We pick one row for now, say number 8 bar, and we'll do 2 number 8 bars, and that's not enough. Then we go to a bigger bar, number 9. We say, okay, 2 number 9 is probably going to be enough. We overkill, right? 2 bigger than 1.59. And then we bring this 2-inch here, 2 number 9 bars, and recompute the section capacity. Turn this design problem to analysis. Okay, so this is very important. All the step 1 to 4 basically give us an estimation of reinforcement. All right, folks, very important, estimation of reinforcement. Given the estimation, select the bars, then we turn the design to analysis problem and recompute A again, and then the whole shebang like we did before, the whole step like we did before, right? And then the final thing to watch out for is the strain in the steel. You have to make sure that the strain is bigger than 0.005, which is tension control. Why that is so important? Because we made assumption at the very beginning that phi equal to 0.9. All right. I had a question from a student yesterday saying, Bob, What if at this point, I realize that my epsilon t is not tension controlled? It might be something else. My answer to that is, at this point, if epsilon t is not tension controlled, that is fine. That is fine. Just use that string value, recompute your phi, recompute your phi, and then recompute your moment. The only thing you might need to worry about is that if your epsilon t is greater than 0.05, tension control were fine. But if epsilon c is between 0.05 and 0.00207, all you have to do is change phi, okay? You do not have to worry about mn calculation because mn has as fy d minus half a, where if your strain steel is between these two, at least you still have the yield strength in the bar, yield strength in the bar. The problem only arrives when your epsilon t is smaller than 0.00207. When that happens, you have choices to make. One choice, like we showed, is recompute your stress in the steel. You cannot use Fy anymore, and that stress in the steel has to be Es multiplied by epsilon s. And in this case, if it's smaller than 0.0207, and mind you, folks, this is for grade 60, and this is smaller than yield strength, but that's fine. When you calculate your moment capacity, it will be As Fs instead of Fy, and this is ds minus half a. All right, so that is the difference. That is a difference. All right, so why I'm bringing this question up, because there's student asking me, what if I have to change the height because, okay, can you guys hear me? Can you guys hear me?
Yeah,
I can hear.
I cut out? Was I cut out? Okay, sorry, where did I cut out? Okay, let me repeat. Let me get this thing closed. Okay, I don't know what's going on with this app thing. Okay, you guys hear me okay?
Yep.
All right,
Yeah.
good deal. Just froze a little bit, right? Go back about 2 minutes. Okay, go back about 2 minutes. Okay, I think I was talking about epsilon t, was I? When epsilon t is greater than 0.005, it got to be tension controlled. Was it? Help me out here, Jordan. Was I
Yeah, that's
there?
where it started getting fuzzy.
Okay, sounds good,
Yeah.
Sophie. Okay, Jordan, all right, let me do that. So let me clear it up, re-say this. This is important, okay? I don't want you guys to mess up in exam number 1. Here, let me clear this up. No worries, we have time today. Okay, so get this whole thing come out. Good. All right, so let's take a look at it, right? Once I have my epsilon t calculate out to be larger than 0.005, I'm okay. Why is that? Because tension control and phi equal to 0.9, and that works out perfectly because I assumed 0.9 to begin with. The problem only arrives when epsilon t is now bigger than 0.05. Then I have 2 scenarios, right? Scenario 1, epsilon t is between 0.002 or 7 and 0.005. This means you can still use Fs equal to Fy, meaning you can still use the old moment equation as Fy ds minus half a. You can do that. You still can, okay? Because the reinforcement yielded at least. But when things happen, epsilon t is smaller than 0.00217, you are in trouble. In the sense that I do not have a yielding stress in the bar anymore. In this case, what you need to do is recompute your stress in the bar, Fs, equal to Young's modulus of Es multiplied by the strain in the steel, and get you the new stress. And mind you that this is definitely lower than the yield strength Fy, definitely lower than the yield strength Fy. So when you calculate your moment capacity, your Mn will be As Fs, okay? ds minus half a, where Fs has to be this actual stress value, no longer your yield strength. All right, folks? And that is the sacrifice we have to be willing to accept. We have to be willing to accept. Okay, okay. At this point, all right, all these things to be done are on the assumption that we fix our cross section and fix our bar size and number of bars. So this is under the 1 foot by 2 foot section. with 2 number 9 bars, and that's it, right? If you really hated the scenario that I do not want have any condition that the bar is not yielding, you have right to choose not to do that. If you want end up with a bar that always yielded, in this case, you need to reduce your reinforcement area. When you reduce your reinforcement area, you have to compute the whole thing all over again, which is a little bit cumbersome, okay? Which is a little bit cumbersome, all right? So I do not recommend to go that route, but you have options, you have options. Okay, I think this is about to clear up some of the missing part from this example. Any questions? Is this clear? Is this clear? Any questions, folks? Come on, I need some feedback. Negative feedback is also feedback.
Isn't the zones below 0.002 would be the compression controlled?
That is correct. So when you have that, what happens? Your phi equal to what? 0.65.
Okay.
Yeah, we prefer under reinforced and transition zone, right? We prefer those two zones. It was never said we cannot allow compression controlled. I mean, we like tension control, fine. We want tension control, we understand that, but not necessarily always you have tension control. Sometimes you have to sacrifice. But once you have a phi equal to 0.65, that kind of balanced it out.
Can
Does that
it
make
be
sense?
greater than 0.65?
Well, no,
like
that's the lower limits, right? It cannot be lower than that.
Okay.
It can be higher than that, but cannot be lower than that.
I mean higher, sorry, I meant higher.
Higher, well, sure, but you see, this is the cutoff, meaning the strain has to be tension, the strain in the steel has to be lower than 0.02. That allows this. Any higher than that, well, of course, phi will go higher. Okay.
Okay.
Yeah. Any other questions, folks? Quite important. You will come across similar problem in exam and practice. Any questions about this? Quiet, silent.
I do. So in terms of in the graph, when you look at it, when you have 0.9, you're under tension control, right? When you have 0.65, you're under compression control, and in the middle, it's transition zone.
That's correct.
Right? What does that mean? Like real life.
Okay.
Example.
So the physical meaning of these three words really coming from the failure state. Okay. So let me rewrite it here before I move forward. Okay. Let me find the best spot here. Maybe this is the best. So, and again, guys, I write it here doesn't mean it's really connected. Okay. But this is more like an independent excerpt here. Okay. So if you really think of it, when I send tension controlled, that means at failure, okay, my strain in the steel always big and approaching a failure strain. And then concrete failed there, okay? This is tension control, meaning that it is tension of the reinforcement governs the failure mode. Now, the word compression control, meaning that at failure, my concrete has busted 0.03, but my steel does not or has not even yielded yet. So it is a concrete compressive failure governs the failure of the beam. Nick, I have to mute you, okay? In case you have any question, you can raise up. And then if it's in between, we call it transition because both of the compression of the concrete and tension of the steel determines the failure state. Is that clear, the one?
Yes, thank you.
Sure, no problem. Okay, now this is one way of differentiate it. Okay, this is one way to differentiate. The other definition, and this is really for your curiosity crowd, not really something that academically, sorry, or practically concerned, but we also call it under reinforced. Okay, under reinforced here, and over reinforced here. Okay, so if still yielded, that means it is under reinforced. It is good, okay? Under reinforced, meaning it's good. And if still hasn't yielded yet, means it's over reinforced, and this is bad. So naturally, under reinforced state covers tension control and transition zone. All right, and this is just some knowledge for you, and you need to know when people talk about it. But this is something we're not going, most likely we're not going to test you on this. We'll test you mainly on this tension control, transition zone, or compression control. Okay. All right. Okay. I hope this is clear. I have to run faster a little bit to finish this example here. So we finished example number 1, and don't forget at the end of it, we check 2 things, right? We have checked 2 things. One is that we check cracking, and you can think of it simply as amount of minimum reinforcement needed for the beam to resist cracking. So when you lift the beam up, it won't fall on you, right? So this equation here is AS mean equal to larger of these 2 equations, okay? Not smaller of, but larger of. And you find the larger value and this governs, cool, fine, right? And I even showed you how the crack's gonna happen. It's probably gonna happen between the lifting points. So that's where you need to be careful about. Then the last but not least is to check detailing. In our case, we're mainly concerned about the minimum beam width. And how do we do that? 2 ways. One is go with table A5, that is on Canvas, in your file folder. You have sizes, you have numbers, you can estimate the minimum beam width. But I strongly urge you to use the calculation we showed from previous lecture, where you actually calculate the beam minimum. And you will need that for your first exam, which I will show some problem examples tonight. Okay. All right, so that is done, right? Not too bad. And we got everything situated. We're happy. And move on to another example of a cantilever beam. First thing first, when you have cantilever beam, the reinforcement has to sit differently. Now, my first victim, Audrey, Mr. Powell. Audrey, you
Yes,
there? Hey, how are you doing?
I'm okay.
Good, good. Quick question. Don't be nervous, okay? So if I have cantilever beam, my reinforcement, it has to be on top or it has to be on the bottom? If I have a cantilever beam, right, it's bending this way. So which side is my tension side?
It's at the bottom.
The bottom will be in compression, unfortunately, right? So which side will be my tension side?
The top.
The top, right? Because I have tension, I have a compression, and finish the coupling moment. So if my tension side is on the top, my bars will be on top or bottom?
The top.
The top, right? So that's right. Don't forget, in the exam, thank you, Audrey. In the exam, we'll ask you where the bar is going to be at. So in the exam, I can tell you right now, I just made a problem this morning, okay? I can tell you right now. So in the exam, I ask you, draw the geometry of the beams, right? For A, case A, you know, you have a cantilever beam, and this is where the reinforcement at. So you draw on the top. And case B, for example, I'm just making things up again, and I have a bending moment right here like this. Sorry, this got to be positive. Positive bending moment like that, and I ask you where the reinforcement is at, you draw on the bottom. Okay, so it really depends on the positive or negative sign of the bending moment determines where the reinforcement is at. Okay, all right, so this is probably worth 5 points, guys, in the first exam. Okay, so pay attention, pay attention. Okay, all right, so that's that. Then we're quickly moving on. We have dead load, we have live load, we demonstrate how we calculate that, and eventually we arrive at a required moment 232 kip-foot. Okay, and I believe somebody asked us another way of calculating this. We demonstrate that as well and come up with the same number. We're happy, we're happy. All right, so with that, now let's start about design process. So we know the total exerted moment has to be 232 kip-foot. So to come up with a design satisfy that requirement, phi mn has to be greater than or equal to mu, that is 232 kip-foot. Okay, so I don't know anything, but I want to use my first equation, step number 1. Okay, step number 1 is to find AS. estimate AS. How to estimate AS? AS should be greater than or equal to mu divided by phi mn, right? But spell out mn, that is phi fy multiplied ds minus half a, ds minus half a. Andrew, Mr. Slinkard, are you there? Andrew, are you there?
Yeah,
All righty. How are you doing, sir?
I'm doing okay.
Oh, that's good. Good to hear. So quick question here, Andrew. So if I have a ds minus half a, I don't know that. What should I put here? If I don't know ds minus half a, what should I put here?
You estimate it with 0.9 times ds.
Exactly. Thank you, Andrew. So that is what we're going to put here, 0.9 ds, right? So with that number, I can carry out my calculation. Then AS has to be greater than or equal to mu, which is 232 kip feet, 232 kip feet, multiplied by 12 inch per foot, convert everything back to inches. Why is that? Because I want AS to be inch squared, okay? Divided by phi, approximately 0.9, multiplied by U strength of 60 KSI. So I keep the KSI unit because of the kips on top. Then multiply 0.9, which is this 0.9 here, ds. What is my ds? I don't know ds, isn't it? But in my head, I now have a picture that my reinforcement, mind you, that's going to be on the top. I don't know anything, but I know the section height is 24 inches. So I'm just going to take a bold guess that concrete cover got to be 2.5 inch since I have only one layer to be estimated. So here, my depth got to be h minus 2.5, and that is 21.5 inches. So here I got 21.5 inch. All right. So from that calculation, I can move on to get my AS. Now AS equal to a 2.66 inch squared. Guys, do you guys get the same number? Ben, Mr. Schaefer, are you there? Are you there?
Yep, I got that as well.
You got that well? Okay, great. Thank you so much. And now we have finally arrived at a reinforcement area of 2.66 inch. Okay, so now what we're going to do is to follow the next step. The next step is to do what? To re-estimate our A and then re-estimate our AS. Not yet here. And then after get our AS, we need to confirm my strain in the rebar to make sure it's yielded, and then come with my phi, and then select the bars, right? After here, select the bars and get my epsilon t, get my phi, then get my mn, then confirm that phi mn has be greater than or equal to mu. Now this part, folks, I'm gonna leave it to you because you already have example from previous problem. Okay, and now this is gonna be your quiz number 6. Okay, that is find, oh, actually design for select bar. Okay, check phi mn. Okay, and I forgot also the following step, you need to make sure AS min is satisfied, and also the beam width, minimum width has to be satisfied. And this, folks, is going to be your quiz number 6. Okay, all right. This is what we talk about, design a reinforcement for a known section dimensions. Any questions so far? Any questions? Guys, anything? Are we okay? Any wondering, any challenging questions? Anything?
Dr. Mo.
Okay, alrighty. Well, okay, so I assume we're fine for now, and I know you have questions later, but we can talk about that. And then before I let you move on, right? Before we move on, I want to go over something, right? So you have seen this. You have seen 2 examples. Is a beam interior or exterior? Okay, got it. So let's say interior exposure. Thank you, Emily. Interior exposure, okay? To keep it same as before, interior exposure, thank you. Now, we have gone through like 1.5 examples how to design a singular reinforced beam. But you keep forgetting, right, where you're doing this. Sometimes we need a flow chart help us understand how we do this. So let me introduce a flow chart, flow of design for singly reinforced section with known, got to be careful here, okay, with known section size or section dimensions, right? So what is the step? What is the step? First step is what? Assume yielding, actually. Assume yielded. Why this is so important? Because I can use T equal to ASFY. All right, and that's how I got the equation to estimate the reinforcement to begin with. Now, with that, I can do is I can get my AS. Okay, estimate my AS. And once I estimate AS, what I do? I can get my tension equal to compression, right? So I can get my A from tension equal to compression. Okay, from tension equal to compression. And I put CC here because all the compression come from the concrete anyway. All right, then after I get my A, what I do? Confirm AS. Basically repeat step 2 again to find your AS. Okay, and then afterwards select bars that has AS provided greater than or equal to the AS computed. All right, select bars given that is satisfied. Then with the selected bars, you turn design into analysis. Turn design into analysis. And what's more important than this is that turn design into analysis is to find actual compressor zone C, yes, and then that is equal to effective compressor zone A divided by beta 1. Okay, why do we need the C? Because we can use our triangle, this is 0.003 equal to epsilon Cu here, and this is dt here, to find the strain in the last layer of the bars, which is in this case one layer, epsilon t, and then from epsilon t you get phi using that famous diagram I keep repeating, and this is 0.65, straight line 0.9, and this is 0.005, and this is 0.002. Okay, so now I got phi, and then last but not least, right? You get a phi mn, make sure that is greater than or equal to mu, but don't forget to check your cracking, which means check AS min and check, excuse me, check the minimum beam width. Okay, and then concrete cover and bar spacing. You need to fix those numbers, right? And then you're done. Okay, so that is the flow process of design a beam. Now this is design a beam with known dimension. Okay, this is design a beam with known dimension. All right, okay, so this is probably something you can use for creep sheet. And all those equations we just wrote down, you can jam them here, jam them here, jam them here, somewhere in the here, here as well. You know, all those equations. Okay, then you can use that for your creep sheet. Okay. Alrighty, any questions, folks? Are we okay here? For design a singly reinforced beam with known section size? Are we okay? All right, silent again. Okay, well, let's see, right? You might have more problem when I give you the practice problem. Okay, so here, let me open up a new lecture today. So today, the main dish is to talk about lecture number 8, a design with unknown section size. Okay. Today we'll talk about term A is design for singly. We're still in the singly domain. Okay, singly reinforced section. Singly reinforced section without section size. Very important. Okay, without the section size. Okay, and this, ladies and gentlemen, is actually a very challenging problem. Okay, now before we do anything, right, let's see what we need to learn today, right? 2 objectives. Objective 1 Okay, we need to understand there are so many new terminology today we're going to introduce you. And that first thing is understand the definition of reinforcement ratio. Reinforcement ratio. Okay, and before you know it, let's just bring it in, right? The reinforcement ratio is actually called rho. Rho, all right? And rho is defined as reinforcement area in terms of cross section divided by the width of the cross section. And mind you that this B here is BW, okay? BW, and this D here is DS, okay? And what is BW? What is DS? Now, if you have a section like this, of course, this is B, and the same time it is BW. If I have a section like this, say a T-beam, now naturally I have BF, means the flange width, and I have web width BW, and in this case, this is BW. And now for I-beam, same thing goes on, this is BW. Now DS meaning is the depth of the section, so it's the total center of the group of the bars, okay? Group of the bar, not DT, but DS, okay? So that is the definition of reinforcement ratio. Definition of reinforcement ratio. Okay. Now that's first thing we need to understand. Oh, objective 1 completed. No, too bad, right? Objective 2. Objective 2, we need to learn to design. Learn to design. Design what? You say design singly reinforced section without section sizes. So you know it, right? You know it. Okay, so how we're going to design? All right, now going back to old topic, right? You remember we have gone through under reinforced, over reinforced, tension control, compression control, transition zone, right? So I'm going to pick my next victim here. Who's on my list? Brennan, Mr. Poole, you had the microphone issue last time. Are you there? Still having a mic problem? Brennan, not responding? Or am I disconnected? Folks, can you guys hear me?
He said he doesn't in the chat.
Okay, let me see that. Still yes. All right. I'll still have to skip you. You're losing a lot of extra credit opportunities, Brendan. I'm just saying. Carson, are you there?
Yeah, I'm here.
Okay, quick question for you, Carson. How are you doing, by the way?
Good. How are you?
Good, good. So when I try to design my beam, right, and I want to have a preferred state and give you options, I have compression controlled, transition, and tension controlled. Tension control, right? Why is that though? Why do I want tension controlled?
Because more of the failure in the beam will be on the reinforcement.
That's
and
right.
that gives you more ductility too.
Exactly. So. Right. That's good. Thank you so much. So that is the reason we want more ductility. Now you were seeing that in just the lecture before we were talking about, I said, you know, you compensated that by strength reduction factor. True. The lower ductility you have, the lower strength reduction factor you have. So to compensate that, but that does not mean we want to have low ductility. Okay, it's just some compromise we have to make. So now we all know that we want a ductile beam, high ductility. All right. So how to make sure we have that? How to make sure we have that? Is it 8? Yes. So 8.1. Let's see, right? So I want us to talk about design state. Design state. So a section looks like this. Section looks like this. You've seen this so many times before. Have a width, have a height, and also have a depth. And I'm going to put 2 symbolic bars representing the reinforcement net. And then I put some strain diagram showing what is the strain diagram look like. And this is what it is, triangle. And the failure strain for concrete is 0.003, and the actual compressive zone size is C, and the reinforcement right here, and the strain in the reinforcement for one layer, I can call them the same epsilon S equal to epsilon T, isn't it? So this is a strain diagram, and you know that to get 20% of free credits, you need to draw the corresponding stress diagram as well. So the stress diagram reads like this, and this top here is 0.85 prime C, and the effective compressive zone is beta 1C. All right, and then the stress in the rebar is going to be Fy tension, like so, and internal forces is going to be Cc concrete equal to 0.85 F prime CAB, and has a distance of half A away from the top fiber. And then last but not least, the tension here, T equal to ASFY. Now, mind you that the distance between the compression and tension has to equal to a ds minus half A, ds minus half A. So this is 5-pointer. Well, I have another 5-pointer, and I have another 5-pointer, and this is called internal forces. When you collect them 3, I give you another extra 5-pointer to make it 20%, right? So that's not too bad. Now, when I have a design state, if I want to start the beam with a tension control limit, I can enforce my strain in the steel, right, to be a higher number. And that number has to be something greater than 0.005 to be tension controlled. If I can make sure my tensile reinforcement hits this number, then I surely have a tension control state in my beam, isn't it? So I call this a choice, or we call it design state. Okay, design state. Now, this magic number ACI picked out for us already. And ACI says, you better use 0.075. I missed the 0 here, folks. 0.0075. So which is a larger number than 0.05. Okay, to make sure that is tension control. So, matter of fact, so much ensure that if I use this number, I can actually calculate my actual compressive zone size C, and using the triangle here, that equal to epsilon Cu divided by epsilon Cu plus epsilon T, which is the strain here. I set it to be 0.05 and multiply by ds. Okay, and bring the number in. This is 0.003 on the top, bottom here 0.003 plus 0.0075, isn't it? And that, ladies and gentlemen, I got a actual compressive zone equal to 0.286 ds. Okay, so that is my actual compressive zone. So much of a compressive zone, in order to get my total compression force, I can then write Cc equal to 0.85 F prime C and beta 1 Cb, beta 1 Cb. And of course, that is equal to 0.85 multiply 0.286. So I got 0.24 beta 1 F prime Cb. And don't forget, this is in terms of ds, this is have a ds. So bring this number in actually into this equation. This is what I got. This is what I got. I got this compression from the concrete. Naturally, I want to balance that with tension. So tension equal to ASFY, and that equal to Cc. So I got a 0.24. Just bring this here, beta 1 F prime C BDS. BDS. All right. So you look at this equation, you probably get lost a little bit. So Bob, what are you doing? What are you doing? What I'm doing is I look at this equation, I see ASFY on the left-hand side. I see ASFY on the left-hand side. I also see 0.24, weird number, by the way, beta 1 F prime C BDS. Now I start to look at these two terms and I start thinking about manipulation, right? And I like math. I just want to play around. So what I do is I put this AS here. I keep this AS here, and I move this BDS. I move this BDS here, right? So I move this BDS here, and then I keep 0.24 F prime C here. Okay, beta 1, don't forget, and divided by Fy. Then I still have this equilibrium. I still have this equation, isn't it? And then I start to look at this 9 is AS divided by BDS. And remember what we said in the beginning of lecture, we introduced a friend, that is the rho reinforcement ratio, is defined 3 lines, right? Defined as AS divided by BDS. So, buddy, right? I got this equal to the reinforcement ratio rho here. I got it. Okay, why you are so excited about? Because now I know if, and I want you guys to write this down, okay? If I want tension controlled design state, is to be maintained or is to be achieved, to be achieved is a better word. I need to have rho equal to a 0.24 f prime c beta 1 divided by fy. And I'm very happy because you look at this equation, right? This equation is universal. What do I mean by universal? It has nothing to do with the section sizes. It has nothing to do with section sizes. So this is a very good design rule here. It's a very good design rule here. But I keep looking at it. I keep looking at it. This 0.24 number is a very strange number. It's a very strange number. I don't want this decimal points or digits, right? It's just too hard to remember. You know, I cannot remember complexity like that. So what I'm going to do, I'm going to dim it down a little bit, reduce a little bit. How am I going to do? I say, look, approximately, right? 0.24, it's kind of like 0.25, isn't it? Yeah, give or take is 0.25. And that, ladies and gentlemen, it is actually 1/4, isn't it? A quarter. So now with that, I can say rho initial, folks pay attention, okay? Rho initial can be equal to, this is different from rho, okay? Rho initial can be equal to 1/4 f prime c beta 1. Okay, so equal to f prime c beta 1 divided by 4fy, or organize a little bit, beta 1/4 multiply f prime c fy. Okay, and then pay attention, folks, here. F prime c divided by fy is a relative strength between concrete and steel, and beta 1/4 is a constant coefficient or constant. Okay, and I call this, folks, I call this the initial design reinforcement ratio. So cool, hey? And this equation is 8.1. Okay, so that means if I bring this at the beginning of design, I am guaranteed to have a tension control state. All right, and if this is not enough, right? ACI said, look, I want to make it more simple, but actually it is more complicated now. We can call it, introduce another thing, it's called reinforcement index. A lot of definition today, folks, okay? Reinforcement index, okay? And this reinforcement index called omega, and omega is defined as rho fy divided by f prime c. You probably figure it by now, right? You put this equation in here, actually, it is just beta 1/4. Isn't it? That should just be 1/4. But nevertheless, this is called reinforcement index. I'm gonna red box this thing, so you know this is important. Okay, and this is 8.2. Okay, why do we have to have this reinforcement index? Because remember what we had before, A or Mn moment equal to AS Fy ds minus half A, isn't it? And then A would equal to AS Fy divided by 0.85 f prime c b Okay, then I'm gonna start playing, right? I want to multiply by a ds and divide by a ds. Okay, why is that? Because when I do that, I can rewrite my equation. Multiply ds divided by ds, this is essentially 1, right? So it's canceled, but I just want to manipulate the equation, right? I want you to see that then A, the effective compressor zone size, become AS divided by BDS. I just move symbols around, okay? Multiply Fy over F prime C, then multiply by D over 0.85. And ladies and gentlemen, I have a very interesting thing here, because these two is rho Fy F prime C, and that is essentially omega, that is reinforcement index, right? So now I can recast my equation. Now A essentially is omega D over 0.85. And let me call this equation, well, not yet. Well, that is the equation for effective compressor zone A. Okay. All right. This is not the end. This is not the end. Okay. With that, with this A like this, I can go back to see my moment equation Mn that equal to AS Fy, and then that is ds minus half A. And then I can bring all this in because A, I have derived the equation for. Shouldn't be ds over 0.85. Yes. Thank you. It is ds. Okay. Thank you very much. And then Mn should equal to ASFY ds minus omega ds divided by 2 multiplied by 0.285. Now, one more equation, right? One more equation, and I promise you'll be done. So Mn equal to ASFY ds, bring this ds out and bring this ds out. I share the same ds, this becomes 1 minus 0.59 omega. Okay, 1 minus 0.59 omega. Okay, and then I can rewrite, again, sorry, okay, rewrite equal to omega f prime c. What is omega? Omega is reinforcement index, don't forget, okay? 1 minus 0.59 omega and b ds squared. And now if I call r, okay, r, which is a new terminology, equal to omega f prime c 1 minus 5.9 omega, and this is called flexure resistance factor. All right, and let's say this equation 8.3. And finally, folks, finally my Mn, basically this is R, hey, it's R, become R B ds squared. R B ds squared, and this is 8.4. Why this is so important? Because folks, right, this is Mn, right? What if I have phi Mn has to be greater than or equal to Mu? That is phi R B ds squared has to be greater than equal to Mu, and then I can have BDS squared, and this is section property basically, right? Only a variable related to the section size had to be greater or equal to Mu divided by phi R. Nice. Why am I so happy? Because folks, now you look at it, right hand side, I have applied moment, I have phi, stress reduction factor, I have R, which is a flexure resistant factor. With this, if I have all these terms from the right hand side, I can determine the section size. I can determine the section size, isn't it? Okay. All right, folks, we're going to stop here, but this equation I want you to remember in your heart was absolutely important meanings. Okay, absolutely important meanings in the design for unknown section size. Remember this. Okay, and we will talk about how we are going to use this for our next problem. Okay, all right. I'm gonna let you go here, and this is it for today. And we'll pick this up on Monday. Like I said, Monday and Wednesday will be short lectures. Be recorded online again. And then if you have any questions, let me know. I'll leave the homework and practice problem tonight as well. Okay. All right. Well, thanks you folks. Please stay behind for any questions.
Will Monday and Wednesday be like a live Zoom lecture or just a recording?
Just a recording. I'm sorry, be a Zoom link like this, and it'll be recorded, posted on YouTube.
Okay.
Yeah, because that way you don't have to rush between classrooms, so you can go to career fair. I hope that will interfere your plan. Is that okay?
Yep.
All righty. Any other questions for me? Dakota, I see. Yeah.
What does
Yeah,
the quiz
when-
do?
Yeah, when's the quiz due? That's gonna be my question.
Quiz.
Quiz
due-
6, yeah.
Yeah, right here. Quiz 6 due. I gave you 2, actually 3 days. Let's do on, well, actually 4 days now. Due on Monday. How about that?
Sounds good.
Anything else, folks?
I just got a question about the homework, but I can wait for a second.
Okay, sure. Nick, you have any questions?
Will this lecture be posted on your YouTube channel?
Yes. All these online lectures I counted right now, it's about, including next 2, 5 lectures only that will be posted on YouTube.
Okay.
Yeah.
I have
Go ahead.
another question. How long do we have for the exam, and how many questions?
I think I said it earlier in the lecture, 4 problems. Hello, can you hear me? 4 problems.
Yeah, I can hear you.
Okay, yeah. Okay, I'm just gonna stop recording so we have